Great, yeah, please. Okay, see that people are getting in. Good evening, everyone. We're going to allow a couple minutes more for everybody to get into the room before we get started here. I'll give one more minute for people to connect before we start. Okay, I think we can go ahead and get started. So good evening, everyone. My name is Andre Franco. I'm a research scientist at Colorado State University. And on behalf of the School of Global Environmental Sustainability, I would like to welcome you all to our November Antarctic lecture. I have a few housekeeping announcements here before we get started. So this event is being recorded. We'll make it available in the next few days in the YouTube channel of the Poudre River Public Library. You are welcome to send your questions using the Q&A function on Zoom. You'll see the button on the bottom of your screen. So you can send your questions through the talk, and we are gonna address those questions with our lecturer today at the end of the talk. So we are very happy today to have here with us Dr. Tyler McKay. He's gonna present his work on microbial landscapes found on Antarctic lake beds. Dr. McKay is a professor of Earth and Planetary Science at the University of New Mexico. He has a bachelor's in geology by Carleton College. He also has a master's in geology from the University of California, Davis, where he also got his PhD in Earth and Planetary Science. So Tyler, thank you very much for accepting our invite and for being here today. We are very pleased to have you talking about the very fascinating work that you do. And the floor is yours.
Excellent. Thank you. Thank you for the invitation. And it's good to be here with you all. I would like to acknowledge in advance, you may hear some cries from the outside. It's also bedtime for 2-year-olds. So we are working with that. So do not be disturbed if there is some commotion. But yeah, I'm excited to share with you some of the work that I've been doing down in Antarctica in the dry valleys, and specifically taking a view that may not be what we first think of when we look at Antarctica, in particular, these dry valley landscapes. And that is what's happening underneath of the ice cover that we're walking across in this photo. Here we are walking across Lake Vanda, heading towards our field camp with a resupply being dropped off. And if we just sort of take this picture, it's really the textbook case of a polar desert with a rocky landscape, some cold-based glaciers in the background coming down into the valley, and this ice cover that we're walking on. But if you go under that ice cover, it's a completely different world. And what we see is a microbial landscape where we have abundant biofilms of cyanobacteria and other microbes, just completely covering this surface and growing into complex shapes that are a product of the relationship between microbial activity, the depositional environment. And for scale, these are maybe 10 centimeters in height, a little checkerboard on the corner. Each of those is 1 centimeter. So when we think about microbial mats, we might think more about charismatic ones like hot springs in Yellowstone. This is Grand Prismatic Spring, which has this fantastic sign that says, "Do not mark the bacterial mats. Don't disrupt their growth." So while this may be a fundamentally different environment, a hot spring on land, it has a lot in common with these microbial landscapes that we're looking at on the beds of the lakes in Antarctica. Just like the hot springs, here we don't have any critters that are burrowing in and digging through the microbial mats, disrupting their growth. It's also a low energy environment where you don't have waves and currents ripping them up. And as a result, even though the means of excluding organisms are very different between a perennially ice-covered lake in Antarctica and a very hot spring in Yellowstone, the end result is the same, that we see this microbially dominated ecosystem covering the environment. So what I want to cover in this talk is to go over what goes into Dry Valley's fieldwork. So how do we actually do this? What are we doing when we're doing diving work in the dry valleys of Antarctica? Then get into some of the broader motivations of like why we go through all this effort. I know they look fantastic, but also there are fundamental scientific reasons to go and work with these ecosystems. And then I want to get a little bit more in depth in one of the driving questions here, which is how are these ecosystems changing in response to changing climate in the region? And so on the side here, we have one of the microbial structures I'll be talking about quite a bit in this talk, which is a columnar microbial structure that if you look on the inside of it, this is an X-ray CT scan of it, you have these white layers, which are actually minerals that are forming inside of this, this structure, giving you a record of how the environment is changing through time. So stay tuned, more on that coming up. So just to give an overview of where we are doing this work, we're looking at the McMurdo Dry Valleys, which is due south of New Zealand. It's one of the ice-free oases in Antarctica where you have a series of mountains that are effectively keeping the polar plateau at bay. You have ice streams that do make their way into the valley, coming in from the polar plateau, feeding glaciers that enter into the valleys. But a lot of the glaciers that we see here are smaller cold-based glaciers that are coming down from the surrounding mountains due to local snowfall. In these valleys, you have net meltwater production during the summer, which floods areas that then have a permanent ice cover that's between 4 and 6 meters thick in places. So it's a fascinating environment that has a wide range of wet, dry, cold environments that can be colonized by these sorts of microbial communities. So one question that I think we need to address getting to this work in Antarctica is how do we actually get there? And the first step is to fly down to the ice. This is one of the view out of our window on the C-17 that we're flying down from New Zealand. On these flights, we really are the cargo. It's not a particularly comfortable or cushy flight, but we get to head down on pallets along with all the cargo that supplies and keeps McMurdo Station running. Once we land on a sea ice runway where we have a shuttle bus waiting to take us to McMurdo Station. We can meet up with some of the folks who are down there before us, who have already started the projects. We can really make use of the infrastructure that has been put in place by the US Antarctic program, and also in a lot of my work is in collaboration with the New Zealand Antarctic program. So both of them share these logistical operations, actually getting people down to Antarctica. So the bases for the US Antarctic program are located only a few miles away from each other. The US base is much larger than the New Zealand base. This is the view from Observation Hill looking down onto the station with some large fuel tanks up here, keeping the station running. And then a whole collection of buildings, dormitories, lab space, logistics operation centers that really facilitate the work. In the summer, it's well over 1,000 people who can be down on this base, really a small town down in Antarctica. The New Zealand station, in contrast, is much smaller. It's only a few hundred people in the peak operations in the summer, and runs a much lighter footprint on the continent, but still does a lot of really fantastic research there. So by pairing these two together, you can really multiply the work that you can do in the region. So we don't stay in McMurdo or Scott Base for very long. We typically get into helicopters and fly out across the Ross Sea or the Ross Ice Shelf, I should say, into the dry valleys of Antarctica. All of our field equipment is taken in by helicopter. Here you can see it being slung beneath a helicopter to be taken out for our camp put in. And then we head out into these dry valleys. So, skip the slide there. So when we first enter into the valleys, we're flying over the mountains and get a bird's eye view of these ice-covered lakes that are the subject of our research. This is Lake Vanda, for example. It's one of the larger of the ice-covered lakes. It's over 70 meters at its deepest. Sorry, having some slide issues there. But then we end up landing in our field camp. We're camping on the land adjacent to these lakes. This is Pierce Valley. And once we're dropped off there, we really are on our own in these polar desert landscapes. And the surroundings are really quite alien. It's a landscape that's dominated by physical processes where you have wind and freeze thaw sculpting the rocks into these abstract shapes. This is a beautiful ventifact where you've hollowed out a granite boulder and just left the rind of it in place. I like to think of it like a breaking wave on the landscape here. And we're not the only critters who have found our way in, but occasionally seals or penguins will wander into the dry valleys. There's nothing there for them to eat, and there's nothing to eat them, so they typically mummify and then are slowly abraded by the wind over years. So from these skeletons, you actually can tell which way the prevailing wind direction is, that they're being scoured by sand. So in this rather desolate but beautiful landscape, we're dropped with our pile of field gear. This is that set of crates that was being slung below the helicopter. And then from that, we set up a field camp with tents for our kitchen, dining facility, workspace. We can have some lab tents set up, the all-important toilet tent that is set up. And then we put up our own personal tents where we spend our time. And typically when we're camping in these dry valleys, we use established campsites that have been the hub of operations for research at each lake for a long period of time. And that really reduces our footprint on the environment. You can see a well-worn path through the middle of this field of view, which is the same path that we used every season that I was here at Lake Joyce and Pierce Valley, just so that we're not crushing the delicate soils of the dry valleys or trampling rocks that are being processed by different depositional processes through long periods of time. And so in that context, we also are doing research. We're setting up labs. If we're working on the ice cover, sometimes we'll have a lab and our dive tent out on the lake ice. This is one that we're setting up with the New Zealand program as a key. If we're wearing orange, we're with the New Zealand program. If we're wearing red, we're with the US program. It's a nice little tell of what program we're with. But here we'll be putting our dive hole in the middle of these two tents where we can bring samples back and do some work on these microbial ecosystems. Some of the other camps are actually a little bit more permanently equipped. This is one of the lab rooms at the Frixell camp, which has dedicated infrastructure for supporting research projects that are coming through the region. So depending on where we are, we may be working in a tent, we may be working in a semi-permanent hut, but all motivated by the research with these microbial ecosystems. So the work that I'm going to be talking about today primarily focuses on some of the setting of Lake Vanda, which is up here in Wright Valley. And most of the research will be focused on Lake Joyce, which is down here in Pierce Valley. And so it's a little valley that comes off of Taylor Glacier. A lot of the long-term research through the LTER in the dry valleys takes place down here in Taylor Valley, which is where you have Lake Bonny, Lake Hoare, and Lake Frixell. So there are a lot of sites down here that have been subject of research for many decades now. So as we're getting started, we need to first take a look at the bottom of the lake in order to figure out where we actually want to focus our research. These lakes are covered by thick ice. So one of the easiest ways to get a first look is to drill a hole with a Jiffy drill. And this is just a sped up video of us drilling one of these holes. We have a drill head on the top and drill flights going down, which we use to penetrate through the ice cover. We pump it to keep the drill bit from freezing in early in the season, and then we pull it out. And I like this video because it shows you how thick that ice is that we are drilling through in order to make observations of the lake bed. So one of the ways that we can make use of these little holes to say something about what's happening underneath is to do drop camera surveys. And one of the approaches I found really useful is doing a camera that has a boom on one side of it. So it's not just a downward facing view. When it goes under the ice cover, I pull on a string and my camera has an oblique view that pulls out to give you a broader vantage looking across the lake bed at what's happening more broadly. So here is one example of one of those oblique views looking now towards that drop camera. This is the camera that we sent down under the ice to kind of guide the descent. Then once we're at the bottom, we deploy that boom and are now looking in towards the axis of rotation as we can twist the coaxial cable that the drop camera is on. And for scale, this camera up here is just about 3 inches across. So watching this video here, we can see that just gives us a sense of what this microbial landscape looks like. We can tell that there are these centimeter scale to decimeter scale pinnacles that coat the lake bottom. Here they are accompanied by the kind of main structure of the pinnacles is covered in a film with lots of delicate webs and other morphological components. I'm just going to play it again because I really like it. But you can see that these are growing in a very low energy environment. These are delicate features. They haven't been crushed by large amounts of sediment. They are growing at 40 meters water depth, 44 meters water depth. And so when we look at a basin like Lake Vanda, we can think that everywhere on the lake bed, up to what we found is around 50 meters depth, there are these pinnacles that are growing and coating the lake bed. If we think about kind of the density that we see in any given spot, from a back of the envelope calculation of lake bed surface area, we're talking about hundreds of millions to billions of pinnacles coating this bottom. So if this were a forest full of trees, it would be a massive forest, but it's on a much smaller scale. We're talking about microbial communities, but again, coating a large area of the lake bed. To dive and actually observe these in place, we need to melt out a dive hole. And the ice is still 3 to 5 meters thick. So it's a lot of work to get down through this and actually access our field site. Typically, it takes about a 55-gallon drum of fuel in order to make our way through the ice cover. This is a metal coil that has heated antifreeze circulated through it on a closed circuit, and the meltwater is pumped out. We have a step ladder to go down and take care of the coil as it's melting, but once you penetrate through the ice cover, the water level will come up to near the surface here. So our diving operations take place with surface supplied air if we're with the US program. Here we have a bank of scuba cylinders on the top that go through a comms box that then gets fed into a tether. So we have a full face mask with voice communications, air supply on the surface, and backup air on our back. If we're with the New Zealand program, usually they actually prefer to do scuba, where you have the tank on your back instead of on the surface, and you do communication by rope pulls instead of by voice. And that typically is the thought to keep your workflows simpler for diving, because we want everything to be very conservative, given that it is such an extreme environment where we are rather isolated for doing diving work. So this is me getting ready for a dive. This is actually at Lake Horror in Taylor Valley with my collaborators Ian Hawes and Anna Youngblood. And we're setting up to do some dives on the ice cover. We have a dive tender who is kitted up, Ian in this case, and he is there to help in case anything goes wrong, but we're generally diving solo because having multiple tethers in the water to have multiple divers would actually lead to greater risk of issue with our, oh, I have audio on this, I guess, so you get to hear me splash. But having multiple divers would lead to greater potential for tangling your tethers, or really just having logistical challenges, keeping track of 2 divers at a time. So if anything happens, we have a diver suited up on the surface with their own scuba kit who can come down and assist. But with voice communications, it makes it like you're really a tight buddy system as it is. So we've gotten down to the bottom of Lake Vanda now. We're looking at these microbial mats. And this is just one example of what the bottoms of these lakes look like. They vary dramatically from lake to lake and at different depths. At the same depth, so this one is at 19 meters depth. If you go a little bit deeper, but still reasonably the same, this is Lake Joyce at the same depth, at 20 meters. And instead of that luxurious microbial landscape, here you see a setting where there's no longer enough light for photosynthesis, and you have slow decay of the microbial mats. In other areas, this is Lake Horror in Taylor Valley. In the shallows, you have so much dissolved gas that you are causing the microbial mats to rip up off of the lake bed and float up into the water column. In other places, like Lake Frixle here at 9 meters depth, you have microbial mats that are growing in a dark, low oxygen environment, where you actually have some of these fantastic environments that have oxygenic photosynthesis taking place in a setting with anoxic water above them and anoxic sediments below them, with just seasonal oxygenation where the mats are getting enough light to do photosynthesis. So we have a huge diversity of environments, from supersaturated dissolved gases to anoxia, from abundant light for photosynthesis to areas that are no longer photosynthetically active and now slowly decomposing. So this diverse landscape gives us a lot of opportunities to ask questions about how these lakes have been changing through time. And once we're down there and we've looked at these microbial mats, we can bring them back up with us. So this is swimming out. I'm on the New Zealand program. You can tell because my tether is just a rope that I've been using for ropeful communications. And so this is in Lake Vanda looking up through the ice cover. When we're down collecting samples, we're putting them into core tubes or Tupperware containers and then bringing up our equipment with us to the surface where we can work on it in labs in more detail and do some more detailed characterization of those microbial deposits. So just slowly ascending here, the last little bit of my ascent out of the dive. And Lake Vanda is particularly pleasant to dive in because you have very thin, clear ice that has about 20% of the light pass through it. So it's kind of our tropical vacation dive site of the dry valleys. But once we have these samples returned to the surface, we take them to our field labs. This is one of my now collaborators, then PhD supervisor, Dawn Sumner from UC Davis. We can bring up core tubes that have been collected to get the microbial mats in their depositional context. Here is one that I've brought up from the bottom of Lake Joyce that is supported by bubbles that are leading to buoyant disruption of the microbial mat. We can also do dissections in the field, do some microscopy, and really get as much context as we can to inform our analyses once we get back to our labs at our research institutions. So here Ian is actually trapping copepods, little sub-millimeter, millimeter scale crustaceans that this was the first time that they've been discovered in the dry valleys. So it was a pretty exciting day when we found them in our microbial mat samples. And here's Anna and Ian doing dissections and labeling microbial mats to take back for molecular sampling to look at actually what microbes are present and what are they doing in these environments. So I've shown a lot of beautiful pictures of microbial mats and talked about how exciting they are, but really, like, what are our motivations here? What motivates us to go to Antarctica, to helicopter into the dry valleys, make a dive hole, go to the bottom of the lake and collect these? And why are we funded to do that? There's a lot of expense and investment that goes into this. So one of the motivating questions here is really, how do these microbial sedimentary records give us insights into an ecosystem that is transitioning through climate change? So these microbial deposits in these lakes are one of the significant ecosystems of Antarctica. And as climate is changing, the lakes that they're in are changing. And by looking at them in their growth environment, we can not only tell how is their activity now changing, but how has their activity changed through time, because these microbial mats give us a long-term record. This is a cut section through one of those microbial mats. This one is from Lake Hoare, where I was jumping in the water that video. And what we see in these mats are wispy layers that are defined by annual meltwater coming into the lake. So these are annual because you have pulses of summer melt that then settles down onto the microbial mats. The mats continue growing and grow up and through the sediments and continue from there. In 2001, there was a major flood year where you had a lot of sediment make its way into the lake. And you can see that in the mat record as this dustier layer in the middle of the microbial mat. So these deposits are actually really valuable, not only for their picture into the microbial ecosystem, but also in a sense giving us a view of what the lake was like in the past. And so, as I've, I think, obliquely mentioned, these lakes are changing a lot. So this is Lake Vanda again. And you can see that since 1947, the lake level, or at least up until 2015 when this was published, lake level went up by over 15 meters. And so if you were a microbial gnat that's making your living on the bottom of a lake, making like photosynthetic activity from the photons that are coming through the ice cover, then through the water column and coming onto the lake bed, this sort of a change in water depth would be a fundamental reorganization of your lived experience. And so in terms of the impacts of our changing climate here, this sort of change in photosynthetic setting is one of the major differences that's happening with changing climate. So we can get kind of a front row seat of this change when we're looking at our field campsites. This is our laboratory tent on the ice at Lake Vanda in 2010. And then by 2013, that site that we were setting up camp is under ice. So there are some camps that are established closer to the shoreline that are needing to be relocated now. So we can really see firsthand how this environment is changing through time. It's not just an abstract historical concept. So I would be remiss if I didn't talk about some of the broader applications as well, since I am in geology and earth and planetary sciences. I think a lot about these microbial ecosystems through the lens of Earth history. And in the near term, from my perspective, I guess, there are paleolake deposits in the dry valleys that give us paleo-environmental records through the last glacial and interglacial cycles to say, what did the terrestrial climate look like in Antarctica during the last glacial maximum, during the interglacial period? And these sorts of work with these modern communities can really help us interpret what we see in these sorts of paleolake deposits from recent glacial interglacial periods. They also give us windows into periods when Earth behaved very differently than it does today. One of those episodes is Snowball Earth, where you had sea ice that extended all the way down to the equator around 700 million years ago. In the middle of this global climate perturbation, you had the first complex life really starting to take root in the Earth system. So our lakes in Antarctica are actually some of the best analogs on Earth today for the habitats that would have been important for the expansion of complex life during these global climate perturbations. In fact, some of the deposits I've been working on from these Snowball Earth episodes are beautiful lacustrine carbonates from dry valley style settings. This is a cut and polish section through one. It's about 700 million years old, and you can see this crinkly texture in the carbonates that shows it was precipitating within microbial mats associated with glacial deposition. So a lot of really beautiful analogs that you can draw between the modern and the ancient. And then the way the microbial mats themselves grow is also hugely important if we want to understand the bulk of Earth history when there weren't larger organisms burrowing in and disrupting microbial communities. So some of the complex and delicate features that we see in these lakes in Antarctica are really our best window into what most environments would have looked like during the Precambrian. And so we can ask a lot of questions here in Antarctica that we can't ask anywhere else. So a case study kind of focusing on one aspect of that, which is recent environmental change at Lake Joyce. This is our view from the shoreline of Lake Joyce. It's about 1 kilometer in diameter, and the lake abuts Taylor Glacier here in Pierce Valley. And so when we were putting together a proposal, I say we, Dale Anderson and Don Sumner, my PhD supervisor, put together a proposal that was my ticket to my first field season in Antarctica. And when they put this proposal together, they had these beautifully documented columnar stromatolites, these growing at the bottom of Lake Joyce, decimeters in scale, coming up off the lake bed with brilliant pigments. And so we were just excited to go and study this microbial ecosystem. And showing up, this is instead what we found. It was a setting where those luxurious microbial mats had been drowned out of their photic zone. They were no longer receiving enough light for photosynthesis, and instead were being coated by sediment and slowly decomposing. So definitely not what we had hoped for in putting that proposal together, but actually a really interesting case study to explore what happens when you transition from a photosynthetically active microbial landscape into one that no longer can sustain those communities. What happens? What record is left behind in the sediments? So to get a sense of what scale this change is happening on, we can look at old aerial photographs and historical imagery to get a sense of when these stromatolites may have lost the light that they needed to grow and what the tempo of that is relative to the history of their growth. So we have here an aerial photograph from 1947, which is our earliest constraints on lake level in Lake Joyce. You can see this beautiful delta complex on one side of the lake and Taylor Glacier on the other. And then by 2016, we look and it has flooded over the delta top and started to expand across the basin floor. So we can compare our aerial photographs to a bathymetric model of the lake that tells us basically when that shoreline would have been at a particular depth. And from that, we can see that since 1947, lake levels have risen by about 20 centimeters per year. So quite dramatically. And so these changes in our lake are happening primarily through meltwater coming in from surrounding glaciers and flooding on top of slightly more salty water that is at depth. So on this figure, what I've shown is an image from the middle of Lake Joyce, where we go from 0 to 50 meters depth. And then specific conductivity here is just a measure for salinity. And so the top 5-6 meters is blocked off because that's where the ice cover is. But below that, we have very fresh water, which is essentially glacial snowmelt or ice melt, as the case may be. And then we have these little steps up in our salinity, which are showing mixing with the saltier water that was underneath when the meltwater started coming in. And so these lakes, as they're rising, are really rising through the addition of water on top, as opposed to, say, flooding and mixing the whole water body. So these stromatolites that we're looking at have been living in this part of the water column for decades now, as the lake is getting deeper on top of them and they're getting less and less light. So in the shallow parts of the lake, I mentioned earlier that there are these really beautiful buoyantly supported structures. This is a bubble that is deforming the microbial mat and suspending it in the water column. We find these at around 8 meters depth in the lake now. And I highlight these not only because they're really cool, but because they'll become very important when it comes to actually interpreting the history of the growth of these stromatolites. So our study on these microbial mats going from a verdant, active ecosystem to one that is slowly decomposing actually really was enabled by finding something unexpected. And so one thing I want to highlight about doing this work in the Dry Valleys is that we never really know what we're going to find when we look in a new lake or in a new part of a lake, because we haven't looked there before. And microbial ecosystems that we're studying are extraordinarily variable, and so can capture all sorts of different aspects of their environment, and really motivates continuing to explore and see new areas of the dry valleys. But I want to focus now in on this case study on one of those stromatolites. So these are those columnar ones that are growing up from the bottom of Lake Joyce. I showed in the title slide where you have a cross-section through an X-ray CT scan, the white being carbonate layers, minerals that are precipitating within the microbial mats. The blues and the reds are sand, mud, and microbial biomass that is also there. And this is just a line drawing of the same diagram, kind of highlighting where you have these carbonate layers. And so these layers of the columnar stromatolite give us a window into how this was growing as the lake around it was changing. So you can think of each of these concentric layers as being one growth surface of the stromatolite. Initially this tall, skinny structure in the middle, then templated by layer after layer of microbial growth, finally transitioning into this more elaborate branched shape that we see. And so if we cut a cross section through one of these, we can see just what makes up this stromatolite. And this is a view looking at the carbonate that makes up the stromatolite. This is a thin section, so it's a slice through the stromatolite that's now cut down to around 50 microns thick, so extraordinarily thin, and viewed under polarized light, cross-polarized light. So the crystals show up as light, and the void space between them is dark, where you just have epoxy. And so the light is showing you where you have these layers of carbonates that have accumulated through the course of stromatolite growth. Now, if we look in these carbonates in detail, at the peak of the innermost layer of the stromatolite, we see these spheres coated in carbonate, and they are carbonate cemented bubbles, which is fantastic. We're actually preserving bubbles that were in the microbial mats at the time that the carbonate precipitated. If we look at them in detail, this is a scanning electron microscope, which I'm going to zoom into here. You can see that these kind of linear shapes are the filaments of cyanobacteria that are preserved in the carbonate. So it's a mesh of cyanobacteria that were trapping these bubbles and then serving as sites for the carbonate to precipitate and mineralize in place. And so when we look at these stromatolites in general, what we should really be seeing is something that was initially very similar to these bubble-supported structures from very shallow parts of the lake, that then were the template that continuing layers of microbial communities grew off of. And so as we're looking at that, we can start to interpret what this might mean for how the lake has changed through time. One of the really fascinating data sets we can pull out of these carbonates, in addition to things like chemistry about the lake and the shape that these were growing in, is microfossils that preserve the microbial community. This is like the most basic, I even hesitate to call it microbiology, but micropaleontology of these communities, because we're just looking at the shapes and diameters of filaments. But in Lake Joyce, it's actually useful because we have some very characteristic differences between different types of cyanobacteria. There's a whole suite of cyanobacteria that have very small diameters. So this is the count of the molds that we have in logs. So 3 would be 1,000 of our cyanobacteria here. And then we have these larger diameter filaments that are consistent with another particular type of cyanobacterium. These larger diameter ones we only really see now in significant abundance in the shallow parts of the lake, whereas these thinner diameter ones are found throughout the lake and proportionally more significant in deeper depths. So if we go into our stromatolites and go from the inside to the outside, which is really saying the oldest to the youngest, or shallow to deep, since we know how the lake is changing through time, we can look at how the proportion of these microfossils change. And what we see, the red is showing you the volume that the microfossils take up. So big ones take up more volume because they're bigger. And the black bars are showing you the count number of them. And so for two different stromatolites here, where I've done a lot of counting of filaments, we see that through time, the larger diameter filaments disappear and we're left with just the finer, smaller diameter filaments making up the microbial mat. And now that's actually fantastic because it gives us this view not only of how the physical environment has been changing through the growth of these stromatolites, going from shallow to deep, constrained by where we see evidence for bubbles nucleating and growing in the mats, but also shows us who's there, what sorts of components of the microbial ecosystem are dominant. So our earliest aerial photographs where we see pictures of the lake and can constrain its water depth, we know that these were growing in just a few meters below the ice cover at a depth where now we see these bubble-supported structures and coated by those larger diameter cyanobacteria, the filamentous Firmicutes morphotypes that we see dominating the stromatolites and also the shallow mats. Through time, we can imagine that there was a period where with lake level rise, we started to get deeper than the limit where bubbles could nucleate. And at that time, we also stopped seeing evidence for bubbles forming within the microbial mats. So we lost those bubble molds. We then transitioned to a period where the stromatolites were growing exclusively with the finer diameter filaments. We have some nice constraints from aerial photographs and water column chemistry of this depth being around 1973. And then we transition to where we observe them in the modern, where they're slowly decomposing and no longer able to get enough light for photosynthesis. And so instead of an active growing surface, we have one that's just slowly being coated by sediment and decomposing. Because they're in 0-degree water, they are essentially in a refrigerator and decomposing very slowly. So I'll note that the depth we have here for transition from photosynthetically active to non-photosynthetic is from our measurements of light levels in 2010. So measuring how much light they actually would have received at different times in this history of lake level rise. So when we look at these stromatolites, we're seeing a community succession going from these smooth mats dominated by the larger diameter Firmicutes autumnale into these other mats that are dominated by other types of cyanobacteria. And the fact that we see this transition in the types of cyanobacteria that are present in shallow and deep water now, and were present in shallow and deep water all the way back in 1947. We also see the same expression of these morphologies with bubbles influencing the mats in similar ways at these different times. It really shows that we have the same succession of communities with depth now as we did back now 70 years ago. And so in terms of thinking about this ecosystem and how much it is likely to be impacted by a changing climate in the region, it actually gives some hope that the processes that we see operating the lake today with these mats varying with depth and the community composition is consistent with what it was 70, 80 years ago when these stromatolites were initially growing. And that as lake level has been rising, that ecosystem and that habitat of different cyanobacteria types have followed it, sort of as a a bathtub ring of habitats following the shallowest part of the lake as its level has risen. So what the future holds for these microbial ecosystems is a good question, and whether they can continue to keep up with changes in the environment. But from what we've seen, they are very robust and able to take advantage of these new submerged areas as habitats for new microbial mat growth. So with that, thank you for journeying with me through these lake beds, looking at the bottoms of the lakes in Antarctica and thinking through what these records can tell us about how the mats are growing and how they may fare in coming decades. But I'd be happy to take some questions. I see some have come up in the chat here, and thank you for your attention.
Right, thank you very much. That was fascinating. Thanks so much. So we do have a good amount of questions here, and I'm going to try to combine them as they touch the same topic. So we have two questions about the type of microbes that you find there. I know that now on your final slides, you mention a lot about the types of cyanobacteria that you find and how they vary in size with depth. And are those part of a food web? Are there any vertebrates that feed on them in those lakes?
Yeah, so the answer depends on which lake you're looking at. So in Lake Joyce, we discovered these copepods that are living there, which are very tiny crustaceans that live inside of the microbial mats and eat them ostensibly. But they're kind of sparse and not that abundant, and they're not found in the other lakes. We do have other invertebrates that live within the microbial mats. We have nematodes and rotifers, tardigrades. So not a very charismatic ecosystem in terms of large-scale organisms. When we're diving, we're the biggest thing by orders of magnitude. So it really is a microbially dominated landscape. Some of these lakes have a lot of diatoms in them. As you go deeper, those actually can become dominant over the cyanobacteria. On this image, you'll see some like brown spots on the tops of these pinnacles, and those are layers of diatoms that are growing on the mat-water interface. So it is a diverse ecosystem, even if it looks relatively simple.
Yeah, and I would argue that nematodes are quite charismatic, actually.
Yes, definitely. Not to offend any they're everywhere. We owe them great respect.
Right. So there are two questions here related to the depth of the lakes. So how does change between seasons? Does the ice depth also change? And if you can attribute the change in depth or the rise in depth to climate change, or is there any other factor playing a role?
Yeah, that's a great question. So both of those. So starting out with the annual variation. So these lakes are closed basin lakes for the most part, where water comes into them, but the only way that it goes out is by either evaporation or sublimation of the ice. And so the lake level itself is a balance between that water in and water out. And so typically we have increased meltwater that's coming in and contributing to the lake level rise. Every year though, during the winter, you have a period of time where you are just ablating off the ice cover or you're evaporating. And so when you come to the lake at the start of the season, it's generally around 20 centimeters lower than it was at the end of the previous season. There's been a lot of really fascinating work putting out loggers to actually watch where the lake level is through time as you have this loss of mass. And then the meltwater comes in during the summer and either refills that space that's missing. If you have extra meltwater, the lake will go up. If you don't have enough water to replace the water that was lost, it will start to go down gradually. So that balance is really critical to the lake level. As far as attributing it to changing climate in the region, since these are closed basin, all that's really changing is that massive water in and massive water out. Lake Joyce does abut the glacier, and so you could think that maybe the glacier is moving a little bit and contributing to that. But if you look at the water column itself, the chemical profile has stayed consistent, showing that it is the expansion of that freshwater lens on top that is driving a lake level rise instead of just like compressing the water body.
Awesome. So another question related to the types of microbial mats and the depth. Are some of those microbial mats better suited for deeper environments, or do they all try to stay closer to the sunlight? I think you touched on some of those aspects.
Yeah. Yeah, so these are very shade adapted communities. They are growing down to 0.1% of ambient light. So what looks dark to us, they can still photosynthesize. Typically, if you were to expose them to a whole bunch of light at once, they wouldn't do very well because they've really acclimated to that low light environment. That said, they're often also growing very slowly in that low light environment. So the limit that we see, there's kind of a hard limit on how deep they can go based on just how much they can fine tune their pigments and machinery to make use of low light levels. But depending on the lake, that limit of where they get enough light to do photosynthesis could be 10 meters or it could be 50 meters. So it all has to do with how much light makes it through the ice cover and how much light penetrates through the water column.
Well, that leads to the other question. So does temperature change with depth too, and how temperature, what's the role of temperature on that? And the other question from the same person, that's Diana. What happens if we step on those mats? Do they break?
You don't want to. So this is, buoyancy control is one of the first things that we really practice when we're going to be working on diving in these lakes. And even thinking about where your fins are, where your fin stroke is going. Because if your fin strokes down and puts a plume of water, it will blow out the microbial mats in that area. So sometimes they're very delicate. I think you're much more kind of a submarine doing ballet when you're working with these microbial mats, and you're like a porpoise swimming through the water. So you tend to try to move very deliberately and slowly. If you're going to be doing a lot of work, you just go into a little fin pivot where your fins are just barely resting on the lake bed. And then to get up, you kind of have one leg come up and just gently help loft you off of the lake bed so you don't kick down and destroy a whole bunch of microbial mat. So these may be crunchy, but they're also very delicate.
Great. So there's a geological question here. How do structures and their environments in the dry valleys compare with those in the pre-Cambrian Shark Bay and the Bahamas?
Yeah. So I would argue that these are actually, in some cases, more analogous to Precambrian stromatolites than what we see in Shark Bay or the Bahamas. In Shark Bay or the Bahamas, we have a lot of algae contributing and a lot of larger scale organisms contributing to the way that they're growing. Whereas here we have really layering that's due to the microbial communities. Some of them are actually our best modern analog for Archean microbial mats. So things that were over 2.5 billion years old before you had oxygen in the atmosphere. I think I actually have a photo of one of those maybe as the next slide here. These are some of them. But you have these really delicate pinnacles and webs, and those are really similar to what we see in some ancient microbial mats long before there was oxygen in Earth's atmosphere.
Interesting. Great. Well, with that, we have covered all the questions that we received here through the Q&A. And that's great because it's 7:29. So we are just about time. Perfect. So with that, Tyler, I want to thank you again. This was really, really interesting. We all learned a lot today. And I want to thank you all for attending the lecture. This closes our program in the fall semester. We are going to be back for the spring, probably February or March, to resume the program. So thank you all. Thanks for the library, for the support. And thank again, Tyler, for for your participation.
Thank you very much.
All right, have a good night. And again, everyone, you can look tomorrow or Thursday for this on the YouTube channel for the Poudre River Public Libraries. Thank you. Have a good night. Bye-bye.